Hi everybody, this is Mr. Folly, and I know my computer crashed last time, so let's hope it doesn't crash this time. We're going to hammer all the way through 3 and 4 since I won't be here for a couple of days. We're going to start with indicators for titrations. An indicator changes at plus or minus 1 pH unit of that pKa of the indicator. Yes, indicators themselves are weak, very weak, acids or bases. So this is key. Any indicator within 1 pH unit is perfect. One is not better than the other. They are perfect. Okay, so the indicators change because remember, one drop. If I graphed it, one drop is like 6, 8, 10, 11, 12 pH units. So any of them would be fine. So you don't really need to memorize any of these indicators, but don't be surprised if you're given a chart like this, and if it said which indicator should you use if pH at equivalence um, is 9.3. So if pH at equivalence is 9.3, I could use this one, I could use this one, I could use this one, I could use this one. So I could use naphthylphthalate alpha, phenolphthalein, cresolphthalein, thymolphthalein. Okay, so as long as it changes within 1 pH unit. Indicators know litmus is something you should be comfortable with. It changes the pH of 7. It changes the pH at 7. And remember, if it is rayed, acid. If it is rayed, acid, and blue is base. Methyl orange or methyl red, if your equivalence point is acidic, then you use methyl orange or methyl red. Phenolphthalein is what we use when the equivalence is basic. Now, here's the thing you should know. Any indicator works for strong. The reason why is if I have something that's weak, it kind of does one of those little deals, right? So it's got a big range in here. But if it's strong, it's like this, whoop, whoop, and then like all of the pH units change in that same spot. Mild exaggeration, but not much. Reactions of indicators. Look at methyl orange. Okay, so I'm looking at methyl orange. Methyl orange. So it changes pH. The middle of its pH change range is, we say these are black and white, welcome to my world, is about 4.7. Okay. So when you add H3O positive, I'm adding something on the right, it would shift to the left, it becomes redder. If I add OH negative, it would steal H3O positive, shifting the reaction to the right, and it becomes yellower. That's it. We didn't get that far, so that was the 3 minutes we missed on the last one. Molecular structure and acids. So if I have the binary acids like HF, acid strength is increased by increasing polarity of the bond to F. So if you remember on your cheesy little periodic table, this is the most electronegative atom, which is fluorine, right? Increased polarity makes the H more attractive to many waters. So see how all these waters go, ooh, hey, 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 oh, I love you. Oh, come, leave that terrible fluorine and come with us. And that's it. Acid strength is decreased by bond strength. So remember, if this bond strength, that is the covalent, it doesn't have to be F, but H to F bond. So if that strength is stronger, then the acid's going to be weaker. Because remember, an acid is supposed to split apart. An acid's strength is increased by bond length. That means it's weaker. So you go back to those trends of the periodic table. These can contradict, so use periodic trends as best you can. Or, and more nonpolar parts reduce acidity. So we're going to get to this part right here, nonpolar parts. What's a nonpolar part? Nonpolar parts are C's and H's. So oxyacids. More O's makes it more acidic. So remember, O is super attractive to electrons. So if I'm looking at HNO3 here, these O's are so attractive to electrons that what happens is they all leave this area and it becomes super amazingly positive. That's why it's so good at separating. So these O's, every O, oh man, there's O's here. The electrons want to go there. So if the pull of the electrons are over here, I'm left with a very positive one. So HBrO3 is stronger than HBrO. Okay, so more oxygens increase polarity and increase Ka. Same is true for nitrogens and maybe other very electronegative atoms like a fluorine or something like that. The number of H's make it more acidic and makes it a bigger Ka by a factor of 10,000 or so. Holy cow, look at this. 10 to the third is the Ka for 3 H's. If I've got 2 H's, 10 to the 8th, that's 5 zeros different. Another H, 5 zeros different. So if I wanted to go from H3PO4 and turn into 3H positive plus PO4 negative 3, that's going to be the product of each of these. So that's going to be 10 to the negative 21, 10 to the, so it's going to be something like e to the negative 24, meaning it ain't happening, my friend. Okay. Also, the pH of Ka2 equals pKa. Sorry for the deep breath. I had my cough, but mind-blowing but true. And we can prove it, but what is the pH of the second one? pKa. So that means the pH of this guy right here is negative log. Oh, I'm without my calculator, but not for long. So here's my calculator. So negative log 6.3 e negative 8 is 7.2. So that would be 7.2 for that one. pH of Ka2. How could I get just HPO4 negative? So the way I could do that is I could have NaH2PO4, right? And Na I would ignore, but that would be my source of just HPO4 negative ions. Okay, so that tells you that it really doesn't happen. So this means the pH determined by the first reaction only. The subsequent additions of H positive are negligible, 10,000 times less. The Ka is different by a power of 3 or more. The only exception is H2SO4. It uses both because the second Ka of HSO4 negative, the Ka is pretty big. It's something like E negative 3. All right. Polyprotic multiple H titrations. Remember, titration is where moles of acid equals moles of base, and it's shown by the inflection point. Bum, bum, bum. If you have multiple H's like H2SO3, you have multiple inflection points. Bum, 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 bum. So also you can have two halfway to titration things. So you can get pKa2 and pKa1. Can you plug me in when you're done? When you take yours off? Or you can sit there if you want. Weaker acids, the second H coming off, has a more gentle inflection point. So remember, all weaker acids have a more gentle inflection point. Ka is found by titration. pH equals pKa at half the equivalence. We did that a lot already. And then we talked about how to find the Ka for those. Buffers, Henderson, Hausebach, we spent a lot of time with this already. The equation is good for moles of A negative and HA, or for molarity. So either one is there. Substantial amounts, and I said within a factor of 100 of each other, right? Or substantial amounts of weak acids and conjugate bases. A trick, the test asks for a strong acid and a base. So if I said I have HCl and Cl negative, not a buffer. Why is it not a buffer? Remember how it's got to be a weak base and it's conjugate acid. This is a strong acid, okay? But if I had like NH4Cl and NH3, then I would be looking at this right here would be a weak acid, and this would be its conjugate base. Or we could flip that around and say base and conjugate acid. If you titrate partway, you get weak acids and conjugate bases. We've done this before. Mix a weak acid with a salt and its conjugate, HF plus NaF. Buffer. Reactions with buffers that remove changes. Okay. Reactions with buffers that remove pH changes the substances. So reactions with buffers that remove pH changing substances. Remember, there's only two things that affect pH. The two things that affect pH are H positive, H3O positive protons, and OH negative. They're the only ones. Okay. So given an HF and an F negative buffer, if I had H3O positive, okay, so what happens is If HF reacts with H3O positive, there's nothing attractive about that same thing there. But, but if I have F negative and H3O positive, remember they're both there, so they're both available to do that. Do you see how H3O positive turns into HF, right? So HF doesn't really affect the pH much. So that's why it's pretty consistent. If I add base to the same system, so a negative and a negative, no reaction. That's just silly. That is just silly. But OH negative and HF, this H is attracted to the OH, so I get water and HF. Okay. Equilibrium problems with buffers. So this was actually in the last big idea, but I like it here a lot better. The concentration of H positive or OH negative will remain constant and will not change by X or minus X in an ice diagram. So FeOH taken twice has a KSP of 2.4 E negative 11. What is the concentration of an Fe plus 2 solution if it's buffered at a pH of 8? So pH is 8, so POH is 6, so OH negative is 1 E negative 6. So I'm going to find the solubility of it. So it's a solid, so I'm going to have some 0, not 0. See how it's not 0? It's buffered at that situation. Minus X plus 2. Plus 2X. It doesn't change. Why doesn't it change? It's buffered. And on the end, I don't care. X. It's still buffered. So that means I plug it in. And 2.4 E negative 11 equals X times 1 E negative 6. Oops, and I did not put that number in there. So let's do that. 2.4 E negative 11 divided by 1 E negative 6 squared is 24. Yeah. 2.4 E negative 11 divided by 1 E negative 6 is 24 molar, and Mr. Folly has a big sad face because that's an impossible number. That's what it says, but I should have picked a different. Excuse me. I should have actually looked up the real molar solubility of iron hydroxide, which I think I'll do right now. Oh, I won't. All right, we're going to assume unlimited buffer capacity if they don't give us a limit on these problems. All right, so let's look at buffer capacity. There is a limit to how much acid or base a buffer can absorb. The limit is calculated in moles. The buffering capacity is best shown by looking at the A negative and HA in Henderson-Hasselbalch. A negative is the moles of conjugate base available to absorb acid. HA is the moles of acid available to absorb the base. Whichever term A negative or HA is larger has a larger buffering capacity. So if I have a buffer that has 0.04 and 0.02, there is more base than acid, so it has a greater capacity to absorb acid. And then if I had if I had a different one where I compare it to this, do you see how I'd have double the top and double the bottom? That's greater capacity for both. It may ask you to do, did you overwhelm the buffer? So overwhelm happens if, in this case, adding 0.06 H3O positive be moles, of that. So if that happened, so if I added 0.06 of that, I would have 0.02 moles of H3O positive in the solution, and then find pH from that. All right, predicting the best buffer. A buffer is good to be plus or minus. So first of all, you need to have buffers of different pHs. Your blood has a buffer that's very close to 7. That way you don't die. Your stomach has a buffer very close to 1. That way it digests food. Okay, so buffers don't have to be at 7. A buffer can be at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 pH. So a buffer is good plus or minus 1 pH unit from the pKa. If I wanted a buffer at 3.5, I could use HF, pKa 314, or HNO2, pKa 339, or formic acid, pKa 3.75, but I have to get the right ratio of A negative to HA to achieve that pH. All right. Comparing parts of acids and bases. So this is stuff you need to have in your mind Very, 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 very fluent with these. Big Ka means more powerful acid. Big Ka means less powerful conjugate base. So remember, if I have a strong acid, my conjugate is weak. Small Ka means a weak acid. But if you're a weaker acid, that means your conjugate is more powerful. Big Kb means a more powerful base and a less powerful conjugate acid. So basically, if you're strong base, you have a weaker conjugate. So you always have, if you're strong, your conjugate's weaker. If you're weak, your conjugate's stronger. Salts are made of two conjugates, and you can predict their acidity or basicity. So NaCl, conjugate of NaOH and HCl, both from strong acids, strong bases. So the conjugates are not conjugate acids or bases at all. What does that mean? pH equals 7. Why is that? Na plus positive plus HOH yields not NaOH. Why doesn't it make NaOH? Because that's a strong base and it has to ionize 100%. So it'll never happen. Now, if I have NaCN, right? Remember how we kind of ignore our always soluble things? Conjugates of NaOH and HCN. CN comes from a weak acid, so it has a powerful conjugate base. So the pH is basic. So here's what you need to get used to. CN negative comes from a weak acid, so it has a powerful conjugate base, so the pH is basic at equivalence, right? Or well, not at equivalence, pH is basic for that salt. Okay, you have to say that. People want to say strong base, weak acid, strong base wins. No, it's not the strong base. It's not sodium. Sodium has nothing to do with it, right? This doesn't happen. I never have. Remember, NaOH, 100% ions. Never together. Okay. Now, if I have NH4 and F, conjugates of NH3 and HF. NH3 has a Kb of 1.8 E negative 5. HF has a Ka of 7.2 E negative 3. HF is stronger than NH3. Compare your K. So, right, stronger acid. So a stronger acid has a weaker base, right? So a stronger acid has a weaker, conjugate base. The weaker base, F negative is a weaker conjugate base than NH4 is a conjugate acid. Okay. The acidic conjugate NH4 makes the solution acidic. Why is NH4 acidic? Answer. F negative is a stronger acid than NH3 is a base. A stronger acid has a weaker conjugate base. NH3 is a weaker base, so it has a more powerful conjugate acid, so the solution is NH4F. Note the base is stronger, so the pH is more basic. This is wrong, no points. Is NaCN comes from a strong base. CN negative comes from a weak acid, so it's going to be basic. Now, if it's multiple choice, you can just say strong base is going to be basic. But a lot of times they ask you why. I think that's the end of it. Woo, 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 woo. Sorry I'm missing you folks, but I will talk to you later. Toodles.